the deep dive. Today we are tackling something that sits right at the intersection of hard math and, well, absolute existential dread.
You're starting with the heavy stuff immediately.
And have to. Because the story we've all been told, the one in the textbooks, it has a terrible ending.
It really does.
According to the standard model of cosmology, what we call ΛCDM, the universe expands faster and faster until the stars burn out, galaxies drift apart, and we end up in the heat death.
Just a cold, empty, dark void. Nothing happens forever. It's the ultimate thermodynamic tragedy, a one-way trip to oblivion.
But, and this is why we are here, we have a paper today that challenges that ending.
A big challenge.
It's titled Scale Variant Cosmology by Ryan Cameron. And the premise is wild. It suggests that the universe isn't just expanding, but that the rulers and clocks we use to measure it are, well, they're slowly drifting.
And if Cameron is right, the heat death is a myth. The Big Bang singularity, that moment where everything is crushed into a single point, that might just be an optical illusion.
And maybe, for our egos, it means we aren't living in some bizarrely special time in cosmic history.
Exactly.
The concept is called βCDM, or βCDM. And the thing I want to stress right up front, because I know we have some skeptics listening, is that this isn't just sci-fi speculation.
No, not at all. It's rigorous. It's a mathematical extension of the standard model. It's testable.
That's the key, right?
It's not magic.
It's a symmetry argument. It proposes that the universe has this fundamental property, scale invariance, that's just slightly broken. And that tiny break, that tiny drift, changes how we interpret everything we see in the sky.
So we're going to find out if the universe is actually playing a trick on us. A trick involving a very specific auditory illusion called a Shepard tone.
We'll get to that.
But before we get to the solution, we need to properly frame the problem. Because ΛCDM, the current standard model, it's incredibly successful, right?
Oh, absolutely. It predicts the cosmic microwave background, the distribution of galaxies, I mean.
Yeah.
It works really, really well.
So why fix what isn't broken? Because it is broken. Just in subtle ways that are starting to become impossible to ignore. The biggest crack is what we call the special epoch problem.
Also known as the coincidence problem.
Right. So picture the standard model. It describes a universe that's basically a battleground between matter, which has gravity, pulls things together.
And dark energy, which pushes things apart.
Exactly. And for billions of years in the early universe, matter won. It completely dominated. That's how we had galaxies. Gravity was winning.
Right.
And for trillions of years in the future, dark energy is going to win completely. Matter will just dilute until it's basically non-existent.
But right now, today, in this exact slice of cosmic history,
They're basically tied. The density of dark energy and the density of matter are comparable.
which is incredibly suspicious. Out of an infinite timeline, why do we happen to exist in the tiny, fleeting sliver of time where these two densities are balanced?
It's like walking into a room and finding a spinning coin balanced perfectly on its edge.
You'd assume someone just put it there, or there's a trick. You don't assume that's the natural state of things.
Precisely. In cosmology, we hold to the Copernican principle, which
Right.
basically says, you are not special.
We aren't the center of anything.
Right. So if your theory requires you to be a special observer at a special time, you should be very, very nervous.
So Cameron's paper argues this coincidence is actually just an artifact of our model. We think we're in a special epoch because our framework is missing a variable.
Exactly. And let's not forget the other elephant in the room, the Hubble tension.
Oh, right. The crisis in cosmology.
Briefly, we have two main ways of measuring how fast the universe is expanding. One method looks at the early universe, the cosmic microwave background,
And the other looks at the late universe. Supernovae, stars near us.
and they don't match. The numbers are close, but they differ by a statistically significant margin, and the standard model is really creaking under that pressure.
So, enter scale variant cosmology. The fix proposed here is scale drift. Now, this is the core concept, so let's unpack it carefully. How does this actually work?
Okay, so the paper introduces a scalar field that mediates a slow, uniform rescaling of dimensionful quantities.
Dimensionful quantities, so we're talking about things with units. Length, time, mass.
Correct. The proposal is that as the universe expands, the very definition of what is a meter or what is a kilogram is evolving. And this drift is parameterized by a coefficient called beta.
And this beta is tiny. The paper suggests it's around 10 to the minus 3, 1 part in 1,000.
It's incredibly subtle. And this is a crucial distinction the author makes, active versus passive units.
Okay.
If I just decide to measure this room in inches instead of feet, that's a passive change. The room doesn't care. Nothing physical changes.
But this is an active change.
Right. This is a dynamical evolution of the metric itself. The fabric of reality is shifting relative to the matter within it. However, and this is the part that keeps it from conflicting with established physics, all dimensionless numbers remain invariant.
Okay, we need to clarify that. A dimensionless number is a pure ratio, right? Like the fine structure constant.
Yes, or the ratio of a proton's mass to an electron's mass. In this model, those ratios are locked. They don't change.
So chemistry is stable, and atom holds together exactly the same way.
Exactly. If you're doing an experiment in a lab or, baking a cake, you would never, ever detect this scale drift.
Because your ruler, your atoms, and your lab equipment are all drifting together.
Precisely. Locally, physics is preserved. The drift only becomes apparent when you look across cosmological distances, because looking out is looking back in time.
So when we look at a galaxy 10 billion light years away, we're looking at light that was emitted when the ruler of the universe was different.
And that changes our interpretation of redshift. Currently, we assume redshift is purely caused by expansion.
The Doppler effect, stretching the light wave.
Right. Cameron argues that part of that redshift is actually due to this scale drift, which means we've been miscalculating distances because we're using a static ruler on a dynamic map.
And when you correct for that drift, the special epoch just goes away.
It disappears. The densities of matter and dark energy don't just cross paths for a moment, they evolve together. We aren't in a lucky time slot anymore.
Now, I can hear the skeptics. It sounds convenient to just add a number to the math to make the problems go away.
A fair critique. Usually, alternative cosmologies add dark fluids or other complex things.
But what I find compelling here is that it constrains itself. It adds just one number, beta.
And it demands to be falsified. This is the section on the linked signature bundle. I love that term.
Sounds like a spy thriller package.
It effectively is a security package for the theory. It prevents you from cheating. Because beta is a global thing, it has to show up everywhere. You can't just tune it to fix one piece of data.
They're all linked, so let's break down the bundle. Where do we look for the fingerprints?
There are 3 distinct places where beta creates a specific logarithmic deviation. The first is the cosmic microwave background, the CMB.
The afterglow of the Big Bang.
Right. In standard physics, its temperature scales linearly with redshift. Q equals T01 plus ZR, a straight line.
And with beta?
It curves. The relationship becomes TOU approx T01 plus ZO to the power of 1 minus beta. It's a tiny, tiny shift.
Yeah.
But if we measure it with extreme precision and find it's just a fraction off that straight line,
That's a smoking gun.
that's smoking gun number 1. The second is in luminosity distance.
Type Eos supernovae are standard candles.
Exactly. We use them to map the universe. This theory predicts they will appear slightly brighter or dimmer at high redshifts than the standard model expects.
And the third one is the holy grail measurement, redshift drift, the Sandage load test.
This is fascinating. We usually measure the universe as a snapshot, but redshift drift is about watching the movie.
So we measure a quasar today, wait 20 years, measure it again, and see if its redshift has changed.
Exactly. We see if it's moving away faster or slower. And βCDM predicts a specific shift in that drift rate compared to the standard model.
And here's the bundle part. A single value of beta, say, 0.01, must fit all 3 of these things perfectly.
You can't use 0.01 for the CMB and 0.05 for the supernovae. If you have to do that, the theory is dead. It's all or nothing.
That rigidity makes it a real scientific hypothesis, not just a just-so story.
It's putting its neck on the block.
And the exciting part is that we're talking about tech we have now. Surveys coming online right now, DSAI, Euclid, Roman, they are designed to get this level of precision.
We are essentially just waiting for the data to download.
Let's pivot to the consequences, because if this is true, the philosophical implications are staggering. The paper uses a specific analogy to explain why the heat death isn't inevitable. The Shepard tone.
This is my favorite part of the paper. It completely reframes thermodynamics.
For those who haven't heard it, a Shepard tone is an auditory illusion. It's a sound that seems like it's constantly rising in pitch, getting higher and higher, but it never actually gets higher.
It's a loop. It's always rising, but never leaves the middle range.
So how does that apply to the universe?
Cameron uses it to explain the difference between co-moving entropy and physical entropy.
Okay, this gets a little technical.
Stay with me. In the standard model, the total information, the co-moving entropy, is conserved. But because the volume of the universe gets huge, the density drops to 0. That's the heat death.
The poker chips are spread too thin across an infinitely large table.
But in this new model, the chips are still spreading out, but the table, the scale, is kind of shrinking or drifting relative to them. So the physical entropy density, what an observer actually experiences, remains constant.
So the universe is the Shepard tone. It's expanding forever, the pitch is rising, but because our scale is drifting, we never actually thin out. We stay in this rich, observable state.
Exactly. It implies a kind of steady-state universe, but without the problems of the old theories. Here, matter isn't created. The metric just rescales to keep the party going.
So the universe would always look full. Stars die, new ones form. It never becomes a cold void.
It removes the dead end. The arrow of time still moves forward locally, but globally, the universe is a perpetual engine. It avoids the thermodynamic graveyard.
Which begs the question, if there's no end, was there a beginning?
Well, the standard model hits a brick wall at the beginning. The singularity, infinite density, physics breaks.
Right, we have the Planck length, the smallest possible distance, but the model says the whole universe was smaller than that.
It's a contradiction. We say, you can't be smaller than a pixel, and then say, the whole movie started inside 1 pixel. It doesn't make sense.
So what's the alternative here?
βCDM offers the solution. Renormalization of the cosmos.
The infinite regress idea.
Right. If scale is relative, there's no absolute bottom pixel. As you look back in time toward the Big Bang, the scale drifts. Your ruler effectively shrinks as you go.
It's like those fractal zoom videos. You zoom into a shape and you see more shapes and you zoom in again and it goes on forever. You never hit a wall.
Exactly. The singularity isn't a physical crash. It's just an optical illusion caused by our static ruler. The paper suggests the universe might not have an origin in the traditional sense. It might just be an infinite scaling history.
That lines up perfectly with the Shepard tone. If you listen to that sound and try to find where it started, you can't.
It's a Copernican principle in time. Not only are we not in a special place in the universe, we aren't in a special time. Now is just as typical as any other moment.
Before we wrap up, we have to touch on the bonus science in the appendix, because Cameron goes even further. He speculates on what matter actually is, and this is where it gets trippy.
This is the emergent matter section. It is speculative, the author is very clear about that, but it's a beautiful idea. He asks, what are particles in this universe?
Yeah, what is an electron in a scale-variant world?
He suggests they might be standing waves or eigenmodes of this drifting scale field.
Like a guitar string. You pluck it, and it can only vibrate at certain frequencies harmonics. You can't have a note in between.
Precisely. The paper suggests that the particles we see, electrons, quarks, are the stable harmonics of the scale field. The reason an electron has a specific mass is the same reason a guitar string has a specific pitch. It's a resonance of the background geometry itself.
Wow, it turns matter into music, essentially. We are just standing waves in a drifting metric.
It connects the very large cosmology with the very small particle physics. It hints they're two sides of the same coin. But again, this is the speculation. The beta coefficient is the hard science.
Okay, so here's the verdict. We have a theory, βCDM. It fixes the heat death, it removes the spooky coincidence of us being here now, and it smooths out the Big Bang. And it does it by adding just one number.
A number we are about to hunt down with new telescopes.
And if the surveys coming out in the next few years show that beta is 0,
then we're back to the standard model. We have to accept the heat death, the coincidence, and all the existential dread that comes with it. The math will have spoken.
But if beta is not 0, if it's, say, 10 to the minus 3...
then we rewrite the textbooks. We have to accept that scale is not absolute, that the universe is dynamic and self-scaling. It would be one of the biggest shifts in our understanding of reality since Einstein.
It really changes how you look at a ruler. It's not just a passive stick of wood. It's a participant in the expansion of the cosmos.
And it's a hopeful theory. It tells us we aren't a fluke. We aren't late to the party, and we aren't leaving early. The universe is a continuous unfolding process that doesn't necessarily have a kill switch.
I like that. The cosmic Shepard tone, the song never ends, it just keeps climbing.
It's a much better alternative to the big freeze.
We'll be watching those survey results very closely. And to you, the listener, I want you to sit with that thought. You aren't a distinct object floating in a void. You might just be a harmonic resonance of the universe itself. That's something to chew on. Thanks for listening to The Deep Dive. We'll see you next time.